In the deep hush of the cosmos, there exist worlds hidden from our eyes, at least at first. For hundreds of years, distant planets lingered as mere whispers, faint shadows and subtle twitches in the glow of distant stars. Yet today, thanks to innovative techniques and advanced tools, these far-flung realms slowly come into focus. We are no longer just discovering exoplanets. We are learning to decipher the stories written in their skies.
Within the luminous shrouds of alien atmospheres, astronomers hunt for hints of untold histories. How do we unravel the mysteries of a planet lying many light years away? We study its atmosphere. That delicate cloak of gas surrounding a planet is far more than simple air. It is the universe's diary, each molecule telling a piece of the tale. The atmosphere holds a planet's autobiography, its origins, geology, climate, and even subtle traces that speak of life or its absence. Interpreting these signals is challenging, but when successful, it reveals whether a world is a blistering giant of gas battered by fierce storms or a serene water world. Sometimes, it offers glimpses of something truly unusual forming within the clouds. No two atmospheres are alike. Each bears the distinct imprint of a planet's past and makeup. Carbon dioxide softly speaks of bygone volcanoes. Water vapor hints at rainfall and seas. And methane may be breathed out by living things or shaped by geological forces. To the trained observer, an atmosphere is a tale written in the language of chemistry. But how do we read this story from so many light years away? The answer lies in light. Though we cannot approach these distant exoplanets, the light they reflect and absorb still reaches us, carrying the secrets of their skies. Encoded within that light are the unique signatures of their atmospheres. With a process known as spectroscopy, scientists separate the starlight and planet light into a spectrum, unraveling it into a rainbow to search for subtle, dark, or bright patterns. These patterns are the fingerprints of specific gases. One powerful method is called transit spectroscopy. As an exoplanet crosses before its star, a transit, a sliver of starlight filters through the planet's atmospheric veil. By comparing the stellar spectrum before, during, and after the transit, astronomers can spot extra absorption at precise wavelengths, evidence of gases in the planet's air. A landmark moment arrived in 2001. The Hubble Space Telescope recorded a transit as the giant planet known as HD 20945b moved across its star. Hubble found a clear fingerprint, sodium gas within the planet's atmosphere. This was the first chemical proof that exoplanet atmospheres could be detected from afar. Pioneer in exoplanet studies Alan Boss observed that this first detection of an extrasolar planet's atmosphere ushered in a fresh chapter in the quest to discover and understand new worlds. With the gates thrown open by transit spectroscopy, Hubble and other observatories began to survey alien skies with regularity. They uncovered sodium in the first hot Jupiter, then found water vapor in others, followed by faint signatures of methane and carbon monoxide. Every discovery was akin to learning a new word in an extraterrestrial language. By the second decade of the 21st century, it became clear that some massive exoplanets possess thick, water-rich clouds, while others are surprisingly transparent and arid. In one remarkable instance, Hubble detected water vapor in the atmosphere of a small, temperate planet named K2-18b. This marked the first observation of water on a world within the habitable zone of its star. K2-18b is a super-Earth with a mass nearly 8 times that of our planet. Its moist atmosphere stirred excitement worldwide. While some researchers suggest it is more akin to a miniature Neptune with a dense hydrogen layer than an Earth twin, the detection of water was undeniably significant. However, transits are not the sole method in play. Another strategy is direct imaging, which employs coronagraphs. Rather than observing the influence of a planet on its star's light, we attempt to see the planet itself. This is a tremendous challenge, as stars can outshine their planets by millions or even billions of times. Yet, when astronomers equip telescopes with specialized devices known as coronagraphs, or deploy entirely separate instruments into space to mask a star's blinding glare, those telescopes become capable of capturing the delicate shimmer emitted by a handful of immense youthful planets. In the year 2008, an extraordinary photograph was unveiled. 4 minute specks of light encircling the distant star HR 8799, essentially the inaugural family snapshot of an exoplanetary system. Over several years, these 4 colossal worlds, each boasting a mass multiple times greater than that of Jupiter, were seen gracefully orbiting their sun, granting humanity a rare glimpse into the intricate design of a foreign solar system. Initially, these direct images did nothing more than chart the locations and paths of the planets themselves. But now, scientists have gained the ability to scrutinize the very light these worlds emit. In the spring of 2025, the James Webb Space Telescope delivered the most detailed infrared views of HR 879 ever recorded. By spreading out the planet's own infrared radiance, JWST exposed that all 4 of these giants are rich in heavy elements, such as carbon and oxygen, with telltale carbon dioxide markers boldly etched into their spectra. This evidence points toward a gradual formation process, where gas slowly gathers around solid cores, much like Jupiter's own birth in our own solar system. By detecting these prominent carbon dioxide signals, researchers have demonstrated there is a substantial concentration of heavier atoms in the atmospheres of these planets, explains astronomer William Balmer, whose team was responsible for analyzing the new images. Through direct imaging spectroscopy, scientists are not merely observing distant worlds, they are essentially sampling their atmospheres. Piece by piece, this technique reveals how planets are assembled from their building blocks. There exists yet another approach, one akin to creating a thermal portrait of a planet. Whenever a planet slips behind its star in an event called a secondary eclipse, astronomers can gauge the decrease in the system's total infrared glow. By measuring these drops at a range of wavelengths, experts map the temperature variations across the planet's dayside, effectively composing a rudimentary weather chart for a remote world. This technique is known as eclipse mapping or phase curve mapping. The results are nothing short of astonishing. With impeccably timed observations and tools such as JWST, investigators discern whether one hemisphere is warmer or cooler, which can hint at swirling winds or cloud layers redistributing the heat. In one of the earliest celebrated efforts, the Spitzer Space Telescope charted the blistering, sunlit hemisphere of exoplanet HD 189733b, discovering a massive hotspot displaced by powerful winds. Today, eclipse mapping has evolved to expose even subtler features, potentially revealing contrasts between land masses and seas on future Earth analogs. Step by step, these methods, transits, direct imaging, eclipse mapping, and more, allow astronomers to probe the atmospheres of far-flung worlds. The evidence may look like faint lines on a chart or minute variations in a star's shine, but for scientists, they represent deep insights. With every spectrum collected, a mere pinpoint of light transforms into a fully realized planet, complete with swirling clouds, placid or tumultuous skies, gentle haze, deadly vapors, still waters, or unseen volcanic eruptions below the surface. And the revolution in what can be achieved is only beginning. So, where do we stand at this moment? Over the last 2 decades, astronomers have assembled a vast album of atmospheric milestones. One landmark after another has illuminated new secrets about these distant realms. In the year 2001, HD 29458b, the archetypal hot Jupiter, disclosed traces of sodium in its air, marking the first ever detection of an exoplanet's atmospheric signature. Thus began the age of remotely exploring alien skies. By 2007, the Hubble and Spitzer space telescopes had identified water vapor on the superheated planet HD 189733b, proving that even blazing gas giants can harbor water vapor above their clouds. Astronomers started to discuss clouds and haze on worlds heated to dazzling intensities. Then, in 2013, Using a ground-based observatory fitted with an ultra-sensitive spectrograph, researchers measured carbon monoxide winds surging through HD 29458b's atmosphere at thousands of miles per hour, the first direct observation of weather on an alien planet. In 2018, data from the Hubble Space Telescope revealed water vapor swirling in the skies of WASP 39b. Just a year later, it made headlines by identifying water on K1218b, a smaller planet residing in the habitable zone. These discoveries offered tantalizing hints that, even far beyond our own solar system, water, the essential ingredient for life, could be relatively widespread among distant worlds. Each new finding added a fresh element to the cosmic recipe book we are building. Over time, astronomers detected a growing roster of molecules and elements: sodium, potassium, water, carbon monoxide, methane, hydrogen, helium, and many others. For a while, this list was shaped by the limitations of earlier instruments, usually favoring species that were easiest to spot on large, hot planets. But then, everything changed with the arrival of the James Webb Space Telescope. Launched in 2021 and fully operational by 2022, JWST began a detailed survey of exoplanet atmospheres. Within its first few months, JWST set its sights on WASP 39b, the same inflated hot Saturn where Hubble had glimpsed water vapor, and uncovered a genuine treasure trove of chemicals swirling above its surface. For the very first time in history, astronomers observed a crisp, unmistakable signature of carbon dioxide in an exoplanet's atmosphere, a telltale peak in the spectrum, precisely where a CO2 fingerprint should appear. The scientific community celebrated. Carbon dioxide is not only widespread on planets, but it is also vital for unraveling a world's history, released into the air by both volcanoes and living things. James Webb did not stop there. As more signals poured in, WASP 39b was shown to harbor sodium, potassium, water vapor, carbon monoxide, and, to everyone's surprise, sulfur dioxide. Spotting sulfur dioxide on a faraway planet was a revelation. It hinted at photochemistry, the kind of light-driven chemical reactions that, on Earth, form our protective ozone. In other words, for the first time, we were witnessing an alien atmosphere actively responding to its star, creating new molecules in real time. The identification of photochemistry in the atmosphere of a hot Jupiter-class exoplanet was a breakthrough, opening up brand new lines of inquiry, according to Professor Natalie Batalla, the leader of the JWST team focused on WASP 39b. For scientists, this was like reading more than a list of chemicals. It was watching the evolving story of a planet's atmosphere unfold before our eyes. Thanks to James Webb, we now hold a complete chemical blueprint of this distant world, with vital clues about its origins. For instance, a high ratio of oxygen to carbon suggests the planet formed far from its star, gathering icy materials as it grew. But JWST's abilities reach even farther. The telescope has now begun to sample the air of rocky, Earth-sized planets. In the TRAPPIST-1 system, located just 39 light-years from us, 7 stony worlds orbit a cool, dim star, making them prime candidates in the search for Earth-like atmospheres. In 2023, JWST targeted the innermost planet, TRAPPIST-1b. The result? It appears almost certain the planet is airless, a parched and exposed rock. Although disappointing, since TRAPPIST-1b's proximity to its star makes it inhospitable, this finding was a technological triumph. James Webb directly measured the planet's heat and discovered that the day side is so blisteringly hot that any thick atmosphere would have moved the heat around or left a clear infrared signature, yet none appeared. All evidence points to TRAPPIST-1b being barren and scorched by the star's relentless radiation. However, its neighboring worlds, especially TRAPPIST-1e, F, and G, are cooler, potentially more welcoming, and are next in line for investigation. Do these siblings possess atmospheres? We are waiting on the edge of our seats to find out. Today, our catalog of exoplanetary atmospheres features hot Jupiters, warm Neptunes, mini-Neptunes, and several likely super-Earths. We have discovered worlds where iron rains from the sky, so hot that metals vaporize and then condense into droplets after sunset. Others are shrouded in clouds made of sand or sulfur. Astronomers have clocked powerful winds, spotted mysterious hazes, and even traced the spectral fingerprints of atoms such as titanium and sodium as they escape into space. Yet, as we decipher the chemistry of distant planets, what exactly are we hoping to uncover? Some gases serve as clues to the processes shaping a world. Take carbon dioxide, for instance. Carbon dioxide can accumulate either through volcanoes unleashing carbon from deep within a planet, or from the dynamic activity of living organisms. Here on Earth, carbon dioxide is a constant presence, courtesy of both erupting volcanoes and the ongoing processes of life, including human activity. When astronomers spot carbon dioxide in a far-off planet's skies, it signals that there are energetic chemical reactions at work, though that alone does not confirm that life exists. Consider Venus, where thick carbon dioxide chokes the atmosphere, yet life is absent. Context is crucial. Take water vapor, H2O, as another example. If scientists observe water vapor swirling in a planet's atmosphere, it suggests there could be clouds or even rainfall. This points to the possibility that temperatures might support liquid water, at least in the upper reaches of the sky. Water vapor was among the very first molecules discovered in the atmospheres of exoplanets, and it remains one of the most frequently detected. On enormous planets, it helps reveal clues about their origins, such as the amount of oxygen they contain. For small, rocky worlds, water vapor is a vital piece in the puzzle of whether a planet could be habitable. However, caution is needed. Even Jupiter hides water deep within its layers, and its presence does not automatically mean a place can support life. Methane, on the other hand, is especially interesting. Most of the methane on Earth is churned out by living things, tiny microbes, and, yes, even cattle, with a small portion coming from geological processes. In an atmosphere rich in oxygen, methane should vanish swiftly because it reacts and breaks down. That is why finding both methane and oxygen together in the atmosphere of a distant planet would be an electrifying hint that life might be at work, since something would have to keep the methane levels topped up against the odds. Scientists are eager to spot this rare combination, but so far it has not appeared. Still, methane has been detected in the atmospheres of several giant exoplanets, primarily on the colder gas giants. This helps scientists confirm, for instance, that the youthful planet known as HR 8799b possesses an atmosphere much like that of a young T-type brown dwarf. Our search list also features oxygen and its close relative, ozone. Free-roaming oxygen is tough to accumulate unless something is constantly generating it, since it loves to form bonds with other elements. On Earth, plentiful O2 is produced by photosynthesis. To date, no one has detected oxygen in any exoplanet's atmosphere, a feat that remains difficult even for the James Webb Space Telescope. Nevertheless, future missions are gearing up to hunt for it on planets resembling Earth that circle nearby stars. A dose of realism is necessary. Even oxygen by itself cannot be called unmistakable evidence of life. In 1990, when NASA's Galileo spacecraft cleverly observed Earth as though it were an alien world, it easily picked up signs of oxygen and even methane in our atmosphere, both strong hints at the presence of life. However, experts cautioned that a planet could, in theory, amass oxygen through non-living means, such as a runaway greenhouse effect where water molecules are broken apart and hydrogen leaks into space. One study conducted on Earth concluded that an oxygen-rich atmosphere alone is not foolproof evidence of living organisms. Ideally, we would want to find it together with other signs, such as methane, seasonal shifts, or unusual chemicals, like the traces left when chlorophyll breaks down, all of which paint a fuller picture. Even sulfur-based chemicals, like sulfur dioxide or hydrogen sulfide, can tell a story. On a volcanic world, sulfur dioxide might erupt from the surface. Or, as seen on the planet WASP-39b, an unexpected presence of sulfur dioxide revealed active photochemistry, reactions sparked by the energy of a star. This shows that the atmosphere is anything but idle. It is a vibrant chemical laboratory. In a way, it is a cosmic kind of smog, created when starlight stirs up the gases. There is no single molecule that declares, beyond any doubt, that life is present. It all hinges on patterns and the broader context. Scientists search for biosignatures, which often means finding pairs or clusters of gases that should not exist side by side unless something, perhaps life, is replenishing one of them. An example is the pairing of oxygen and methane. Another is nitrous oxide, also called laughing gas, which is produced by microorganisms alongside oxygen. In contrast, so-called geosignatures can reveal the geological vitality of a planet. For instance, a combination of sulfur dioxide and water may point to volcanic steam, while large quantities of carbon monoxide mixed with hydrogen could suggest a planet that has undergone extreme heating. As researchers continue to gather atmospheric snapshots from an ever-growing collection of worlds, they are learning to recognize which chemical combinations indicate a lifeless planet and which ones quietly hint, perhaps, at the possibility of life. While the James Webb Space Telescope continues to dazzle, astronomers are already laying the groundwork for the next era of planetary exploration. At the forefront stands Ariel, a mission brought to life by the European Space Agency, poised for its journey in the year 2029. Ariel's purpose is singular and bold, to analyze the atmospheres of approximately 1,000 exoplanets. Its gaze will turn toward warm and hot worlds, ranging from searing rocky terrains to sub-Neptunes and gas giants, all to unlock the secrets hidden in their skies. Armed with cutting-edge spectrometers, this spacecraft will methodically study planet after planet as they pass in front of their stars, assembling the first truly comprehensive catalog of exoplanetary atmospheres. Professor Giovanna Tonetti, who leads this ambitious project, describes it as a cosmic census, one designed to unravel how worlds with varying chemical compositions come into being and transform. Why do some planets harbor plentiful water and carbon dioxide, while others possess almost none at all? In the same period, NASA is preparing for the launch of the Nancy Grace Roman Space Telescope. Its primary mission is to capture sweeping vistas of the universe, but nestled within its payload lies a groundbreaking coronagraph. This device, the most sophisticated ever sent beyond Earth, will strive to directly image planets millions upon millions of times dimmer than their parent stars, and even extract their spectra. For the first time, we might witness exoplanets in visible light, and perhaps discern weather patterns or clouds drifting across their atmospheres. Such progress marks an essential milestone on the path to missions that could one day capture photographs of a distant Earth twin. Meanwhile, efforts continue on our home planet. Construction moves forward on gigantic observatories like the extremely large telescope in Chile, boasting a mirror 128 feet across. NASA will leverage state-of-the-art optics and highly detailed spectroscopy to probe molecules in alien atmospheres, inching ever closer to detecting biosignatures on planets resembling Earth orbiting nearby stars. Peering farther into the future, in the decade of the 2040s, initiatives such as NASA's Habitable Worlds Observatory, the envisioned heir to the James Webb Space Telescope, will strive to capture direct images of Earth-like exoplanets, searching for the faintest hints of life in their skies. Each successive mission stands on the shoulders of its forerunners, moving us ever nearer to the ultimate goal. This is innovation as a relay, passing the torch from Hubble's first glimpses, through Spitzer and ground-based telescopes that sharpened the picture, to the rich atmospheric diversity unveiled by James Webb. Ariel will probe even deeper, and Roman will blaze new trails. With every fresh telescope, every observed transit, every collected spectrum, our vision of distant worlds sharpens. Perhaps, as we look up tonight, a star overhead hosts a planet, beneath a sky not unlike our own. That world has yet to be found, but we are drawing closer, step by step. Each new observation enhances our talent for detecting the subtle signatures that distinguish the familiar from the unknown. The discovery of an Earth-like exoplanet's atmosphere may astonish us. It might reveal traces of pollution or a mix of gases that challenges our very definition of life. Or one quiet day, a telescope may unveil an atmosphere that is undeniably familiar, a gentle balance of nitrogen, oxygen, water vapor, and reactive methane. When that happens and an alien world whispers, "This place could be home," how will we answer? The answer is out there, hidden in the starlight that streams through foreign skies. It is an answer we are only now beginning to grasp.